going to first shorter review rotations of the Earth rotation axis. So is the first one is precession. If I'm not sure if I have read the correct spelling, but it doesn't matter. And if you have sun here, this is the ecliptic. Ecliptic is the plane that this Earth is moving or moving around the sun. So there's a trajectory or the orbit. If you look, the Earth's rotation axis is in this position like that. So this creates the seasons because of this rotation axis. And why this rotation axis is so? That's the question that we are going to discuss actually. And as you know, when the Earth gets closer to the sun, in this problem we have summer revolution. Then we have the longest day of the year. And then when this goes there, we come to a point that we have equal, the length of the day and night is equal. It's called as a descending node. When it comes to the part is called winter revolution. And then come back here to the other part is called ascending node. When the Earth starts going up from the equatorial plate. And this curve is also called vernal equinoxes, which means that again the lengths of the day and night is equal. 12 hours day, 12 hours night. So as you see, when you go upward in that way, the length of day increases until it comes to maximum and then reduces up to comes to equal, and then reduces the nights getting longer up to this winter revolution, which is longer nights of the year. And again, when it goes upward, it comes to a place which the length of the day and night are equal, and thereafter, yeah, this is a circle. And all of these things are happening because of this rotation. What is that? Probably you have seen spinner. You have played with the spinner. When you rotate this spinner on the surface of the Earth, it rotates when the speed is high. You see the rotation axis of the spinner is constant, and after a while, when the speed decreases, the spinner rotation axis starts rotating like this. This means that the spinner will be like this. And this rotation axis is moving around that. And this is because the rotation, the speed of the rotation is, when it is increased, the gravity comes in. and gravity can affect the body of this spinner, and it doesn't let this axis to be vertical completely until the spinner falls down. It is exactly the same for the Earth. Earth Earth is a rotating object. It is rotating around the rotation axis. And after years, due to the gravitation of the sun, this rotation axis starts moving and create a cone. So this is the Earth's rotation axis. This is rotation. And it takes 26,000 years to complete one revolution. This means that 13,000 years later, the Earth's rotation axis will be in that direction. And when we have now summer, 30,000 years later, we will have winter. It is like that. It's this movement, this type of movement, which is due to the gravitation of sun, is called precession. So that's not the only one. Let me consider this, draw this one, this Earth's rotation axis of the Earth. We have moon as well, which is moving around the Earth. And the gravitation of moon also affects this rotation axis of the Earth. This causes that the Earth's rotation axis moves like that during these 26,000 hours. Each small rotation of this one is called nutation. So nutation is due to the moon. And it takes 18.61 years to complete one small circle. So it is faster. And this is the reason that when we analyze the tidal measurement for determining mean sea level, we have to track 18.61 years of data in our analysis to determine the mean sea level. And we have another rotation in the experiment. The reason is that some parts of the Earth is not homogeneous. Some parts are lighter and some parts are heavier. And we have this movement, and in addition to that, due to this non-homogeneity or heterogeneity, we will have small variations along this movement as well. This small variation is named polar motion. Polar motion is faster. It's 435 days. Chandlerian is called Chandlerian period. So we have three movements in the Earth's rotation axis. One is precession due to the sun, nutation due to the moon, and polar motion, which is faster than the others, is based on the non-homogeneity of the mass of the Earth. Some parts are heavier, some parts are lighter, and it causes extra movements in the rotation, polar motion, in the Earth's rotation axis. So, why these things are important? So, because let me explain right importance. When we want to use satellite like GOES or something from the measure the Earth, this satellite is moving along the orbit, and the coordinate of this satellite is determined based on the center of the coordinate system of the Earth's coordinate system. However, this movement and the theories that we are using for determining the orbit on this are based on this, that this space is an inertial space. It means that in that space we do not have any force affecting the satellite. But in reality, we have forces. And the first force is from sun, which affect this Earth's rotation axis. Coordinate system should be fixed in the space. It shouldn't change by anything, it should be fixed all the time. And we see that the sun can affect this Earth's rotation axis, which is in fact the Z axis of the system. Earth's rotation axis. Earth's rotation axis is the Z axis. So if it changes, then the X and Y axis will change. That's pretty clear. So therefore we have to compute the effect of these movements, compute them and remove them from the Z-axis to make it fixed in this space. So based on this, we can have some transformation. I will write, for example, the coordinates vector in international terrestrial reference frame can be a rotation, which is function of time, a matrix of rotation, and we have nutation, the polar motion. This is nutation, and P is precession. And we come to the coordinates in a celestial system. It's called geodetic celestial reference frame. These are the places at the surface of the Earth. This is a coordinate in this space. But I missed something here. There is another rotation here, which I call RC is the rotation around Z-axis, is the GAST. GAST is Greenwich, apparent serial time. So you need to do 4 transformations to transform the coordinate from ITRF system I to CTRF or geodetic CTRF, or geocentric CTRF. So this is the first important thing that you need to consider for when for the satellite geodesy physics and for determining the gravity field. Another issue is also review of Kepler's law. So the first law is that